if you could give a quick introduction about your background.
Absolutely.
And
yeah, thank you very much. I'm assuming that y'all can see my charts.
We can see them, and you can control them.
Excellent. And again, I'm going to preface this by saying I'm on a headset, which hopefully the battery's not going to die on. So if I suddenly drop out, send me a message.
Yeah, we'll do.
Okay. My name is Karen Pickering. I'm the group lead and technology lead for water recovery systems here at Johnson Space Center. I've been working in technology development of water treatment systems for about the last 15, 16 years. My background is in civil and environmental engineering. I did my undergrad at Texas A&M University and then did my graduate work at Rice University here in Houston, specializing in water treatment systems. And I'll tell you, most people don't go to school intending to go treat wastewater for NASA, but things worked out great, and that's what I do now. So my presentation is really two parts. I'm going to talk a little bit about current water recovery systems and then move into exploration systems. This has been sort of a last-minute scramble, so what I've done is I've combined two presentations I've given previously, so if it looks a little choppy, I have to apologize for that. But hopefully I'll be able to give you a complete picture of what we're doing in water recovery systems as an outgrowth from what Bob presented to y'all yesterday. Okay, so on to my second slide. Right now we have the International Space Station on orbit, and what I want to talk a little bit about are what are the sources of our potable water on space station, and how does the crew interface to water, and then how do we design our systems to minimize the risk to our crew. This is a chart you may have seen in some of the earlier presentations. I know that you just heard Ray Wheeler with biological processes, and I think he also likes this chart. But this gives you a sense of an integrated, what we call ECLIS, environmental control and life support system, with the crew in the center. And I always like this chart because it's got three little rats over on the side, as if it were the flight experiments we have. But in blue, you see the water recovery system going from wastewater to potable water and how the crew interfaces to that. But it also shows you the interfaces of the water system with the rest of the environmental control system, because you really can't design just a water system. You have to consider how it interfaces to the other systems. A lot of the areas we worry about right now are how we interface to the habitation systems. I believe you've heard from Jim Broyan, because how we get water from showers and laundries and things like that matters as well. I always like to show this slide. It's the human life support requirements. This is my way of saying that water, of course, is the center of the universe. Water is about, if you looked at it strictly from an open-loop water life support system where you don't recycle or regenerate any of your supplies, water is by far the largest percentage of by mass, of your life support needs. We take about close to 90% of the total mass of life support requirements. It's not the one that when you run out, your crew's going to see an immediate effect, like running out of oxygen, but it certainly is a rate-limiting factor for how long you can stay in space without some kind of recycling. So on space station, we have two sources of potable water. We have stored water as well as recovered water. And up until we retired the space shuttle, we transferred a great deal of potable water from the space shuttle. The space shuttle, as Bob talked about in their history, made water through the use of fuel cells. The fuel cells, in the course of creating electricity, make water as a byproduct, which was just stored. Today, because we don't have the ready access to the water generated on orbit from the space shuttle, we launch water in either a Russian Progress vehicle. We can also launch water on the ATV, which is the European Space Agency cargo vehicle, and the HTV, which is the Japanese Space Agency's vehicle. So now we've supplied either tanks or big floppy bags full of water. This is one of the areas, and I love this photograph. My group here at Johnson Space Center provides water containers for use on space station. We originally called them contingency water containers, or CWCs, and they look like giant body pillows on orbit. And you can see we have something called a a water wall, basically. It actually is referred to as a water wall on the space station, where the crew has bungee corded a whole ton of bags full of water into a single area. They're all carefully labeled. These look like big duffel bags. The green are technical water. It's a particular type of water that doesn't have certain chemicals added. Blue is potable in this photograph, and then you can see yellow is waste, and brown is a condensate bag, which is a waste, but a waste that you can recover. As I said, these were originally intended for our contingency use, but they've rapidly become non-contingency. They are used as a normal course of the day. What these are, they have my technical name, a laminated polymer bladder with a Nomex restraint. Basically, you have a big bag of plastic that's heat sealed together on the inside, shaped just like a duffel bag in this case. And then because you could potentially pressurize these bags, then the white material is Nomex, and that provides our pressure support. We call it a restraint to that soft bag, because the soft bag really isn't strong enough to carry pressure. The outer shell is what does it for us. We use silver as a disinfectant for this water because it's compatible with Russian systems, and they hold about 45 liters of water. Now, when we went to the United States segment on the ISS, we shifted. The CWCs are actually kind of retired. We don't fly those much anymore. We're not building them anymore. What we now fly are contingency water containers, iodine, or CWCIs. These are what we resupply regularly. This is what we launch right now, full of water on board the Japanese vehicle HTV. There are approximately 150 of these things floating around Space Station right now, and these look more like a household pillow. They really are a pillow. They're two-dimensional. They have a Teflon bladder. We had to change the plastic we made them out of because the old material was compatible with silver but not with iodine. Iodine is an ion similar to chlorine on board that we use in our municipal systems. I- has a tendency to be absorbed by a lot of materials. One of the few materials that is not absorbed by is Teflon. So we shifted to Teflon and built these more pillowcase-shaped restraints to hold them. So in this case, we use iodine, which is compatible with our U.S. water system, and they hold about 22 liters. They're half as big as our CWCs. That's because the company that makes these, the machining was just not practical above 22 liters. So that's why they're smaller. And now we have water walls full of these type of containers. And here we've got a picture of the crew on orbit working with the CWCI, and you can kind of get a sense of the size of it. You can see there, we always tell them the handle on it is not really a handle. We've put soft straps on there to let them carry it. We don't want them to use that metal piece. That's where the connectors are. If you were to drag a CWC around using that kind of as a leash or your handle, the twist you would get on the fittings that attach that metal pipe to the bag can tend to tear. So we always tell them this is not a handle, and they're real good about not grabbing it now and twisting that. We are currently in the process, actually, with these CWCIs of building some, we call them modification kits. We're building some plastic brackets that the crew will be able to snap onto those bags to protect the places they're prone to break from twisting and breaking and getting caught on each other to try to prevent leakage on orbit. That's the one thing we do find with these water containers. They're very convenient. They're soft. They can be stored flat when they're empty. However, plastic does have a tendency to wear out and leak eventually. If you can imagine, you bring a goldfish home from the store in a Ziploc bag, but after a while you need to put that goldfish into a real bowl because eventually that bag will leak. And that's similar to how these bags are. They do have a limited life. They won't work indefinitely. Okay, so the interesting part on station is the recovered water side of things. The water requirements that's really interesting in a spacecraft water cycle is that they vary as missions mature. and our wastewater characteristics change. Right now on Space Station, we are recovering two sources of water. We're recovering humidity condensate, which makes about half of our wastewater. That comes from sweat generated by the crew that we capture from the air in the space station equivalent of the air conditioner, which, your air conditioner drips water. We capture that dripping on orbit and collect that as humidity condensate. So crew sweat, and then when the crew, quote, showers, although they don't shower, they just basically use, kind of camp towel showers or wet wipes. They'll hang their towels up to dry, and the water that evaporates from those towels is also collected in our humidity condensate. The other half of our wastewater on Space Station is urine. That water consists of crew urine, what we call our stabilization agent to prevent microbial breakdown of that urine, and then the water we flush our waste collection systems with. So our water composition right now is about half and half. So right now on Space Station, this is our process diagram. The urine is treated through distillation. We recover right now 70% of our urine as, we call it, distillate. The other 30% of the urine is discarded as brine. Originally, when we were developing the systems for Space Station, distillation systems were expected to reach about 85% recovery. And this is where I probably start talking too much about urine and gross things, but we'll get over that. We've done all of our ground testing of our water recovery system using urine donated by our friends and coworkers, who generally respond to pleas for wastewater very generously. They tend, at times, people have gone off and drank a lot of water so we can have enough urine to do our testing. What that results in is that our urine is pretty dilute sometimes in our ground testing. So we had hoped to achieve 85% recovery, but right now on Space Station we're achieving about 70% recovery. It's limited, as y'all know, when you boil a pot of water. Eventually you get solids at the bottom when you boil too much of it off. What we don't want to happen is have solids boil off, solids remaining. So we don't boil off so much water that goes to that point. And I guess I should back up and make sure that distillation is basically boiling water and capturing that vapor that comes off of the water and condensing it. And then the rest is, we call it brine. It's the concentrated waste that's left behind. Then the other part of our water, that other 50% that we call humidity condensate, is treated through an ion exchange and absorption process. This uses commercial ion exchange resins that take out the charged components of our wastewater, the salt and the chloride, the sodiums, all those charged ions that we would see in urine or from sweat would come out here. We also combine our distillate. The 70% gets treated through this ion exchange absorption. The absorption is done using granular activated carbon. That is very good at removing organic contaminants, bigger molecules, things that ion exchange would not take up. For instance, if you were to somehow get a little bit of soap into your wastewater, the granular activated carbon could take that out. All the water is recovered through this ion exchange absorption process and goes through a catalytic oxidation process. This is used just to remove the residual organic material. It's a high temperature, high pressure process that basically burns up the remaining organics. And then we have disinfection and storage of the potable water. So that's a process diagram. But let's look at what the hardware really looks like. I'm not even going to try and go through all these green arrows because they're pretty back and forth. This is what we call our regen, or regenerative ECLSS hardware. This system was built at Marshall Space Flight Center, where Bob Agdigian is from, who presented to y'all yesterday. His team at Marshall built the hardware for Station. And we house the water recovery systems in what we call two racks that we keep everything in. And as you can see, it's incredibly densely packed. We replace things. You obviously can't get in there with your hands in microgravity and replace little parts. So we have really this all modularized where you replace a giant chunk. You can pull it out and replace an entire module of a piece of the system. For instance, hopefully y'all can see my mouse. Right here is our urine processor. You can see the urine processor comes in here. It's buried back in there, but that's what we call our distillation system. Coming out of here is the waste from our distillation system, and we have to discard that. That gets all stored, and right now on Space Station is not recovered. Then over here, these cylindrical circle things you see sitting up here, those are our ion exchange absorption racks. So you can see it's a pretty complex system. There's a lot of filter units designed for replacement and change out, a lot of electronics and a lot of cooling as well. We also interface over here to the oxygen generation system, the OGS, because the oxygen generation system on Space Station, of course, uses water to generate oxygen for the crew. I am not going to go through a lot of the details of the urine processor assembly, but this is the crew on orbit on a prior mission about a year and a half ago. We had a problem on the distillation assembly. It broke after about 3 months of operation because of that solids formation in the system. Because we're in microgravity, our solids, our particles, don't settle to the ground like they would on Earth. They continue to float around. They plug the small ports inside of that unit. So the crew was asked to change out that distillation assembly and install a new one, and that's the smiling, happy astronaut who was doing that task. Behind him, you can see some white bags in here. Those are the cargo bags we use to transfer a lot of cargo. Those are not water bags. They're called cargo transfer bags. And those are where his replacement parts are down there, and he returned that unit to the ground for refurbishment. That giant piece he has right here is what's called the distillation assembly. The way that works, instead of just having simply a pot of water boiling on the stove, the crew has this spinning drum, basically, that's at a vacuum. And y'all have all done the experiment where you put water in a bell jar and pull the pressure down closer to vacuum, and water boils really rapidly. That's essentially what's happening on Space Station. But instead of having our bell jar, we have this big cylindrical item. And due to the lack of gravity in space, the microgravity environment, we spin this pretty fast, which creates the force to stick the water to the walls and create our own little gravity system inside of there. That way we can manage the fluid. The water, the liquid water stays on the walls of that system as it spins, and the evaporating water gets drawn to the center and pulled off to be condensed outside of that distillation assembly. This is the entire water processor assembly. Again, I'm not going to really go through the details of this except to kind of walk you through the steps it takes. So we bring wastewater into a wastewater tank, and it looks like a big old tank. It's a cylindrical tank. Inside of that tank, though, is a metal bellows, because, again, the tank, if you just use a plain tank on orbit, the water and the air are going to mix and all slosh around, and you would not get water out of it. You would get a mixture of air and water. So instead of having a mixture, we have a bellows tank that's pressurized on one side, and that bellows expands back and forth with the water volume. Because it's hard to keep all the air out of the system, we have we call it a mostly liquid separator. That's really what we call it, because it is mostly liquid, and we pull a little bit of air off to go back to the cabin. We have a filter unit, and then here we go to those ion exchange absorption beds that you can see up here. Again, heat exchangers, these are the components. Excuse me. And then through another gas liquid separator and into that final oxidation reactor that removes the last of the organic material. We have a polishing bed at the very end. It's an ion exchange bed. Sometimes when you break down the last of the organics, you aren't able to oxidize it all the way to carbon dioxide. You leave some small charged alcohol-type compounds, small carbon chains, and we take those out here in that ion exchange bed. So those come out there, and we now have potable water. The advantage to this system, and it's really pretty elegant, this is high temperature. It runs at about 260 degrees Fahrenheit. But because we're above the boiling point of water, we keep it at pressure. But this has the effect basically of sterilizing our water. So any bacteria that might have made it through are killed at this point. And so we have sterile water downstream of this point. We go to a product water tank where we store our potable water, and we also have this microbial check valve that allows us to iodinate water for storage. Once we have potable water, we have to get that out to the crew. So we have what's called a potable water dispenser, and Jim may have talked this a little bit, but I'm also going to hit on it. This hardware was built at Johnson Space Center by a team that's just down the hall from me. It is basically the way you inject water into the crew's drink and food bags. And right there is where the needles are, and you've probably seen those silver drink bags that the crew has. That's how the water gets injected into that, through a needle right here. The crew can select the quantities of water to inject into whatever container they have. The key here, though, too, is that this system contains a deiodination filter. We use iodine as our disinfectant, which is very, very effective on orbit. However, we had done some long-duration testing here in the late 90s at Johnson Space Center and discovered that even short-duration consumption of iodine ended up having some thyroid effects for the crew. So now we remove all of the iodine from the water before the crew consumes it to prevent any thyroid implications. So we take the iodine out, and we have installed a 0.2 micron filter, which basically provides a sterile barrier for potable water at the outlet, so that we are ensuring that the crew has safe water to drink at that point.
Hi, Karen. I have a quick question.
Yeah.
I was wondering, so if I recall correctly, the water from the dispenser is usually hot when it comes out, and the crew has to cool it elsewhere. Is that correct, or are you able to vary the temperature of the water coming out of the dispenser?
On the PWD that we have right now, we can have ambient water, or we can there's cooler water and warmer water. There is, I'm trying to see if you can see it on this. There's a selection that allows them to pick the temperature of the water in this case. So we do give them some choices of hot and ambient water. It's not really cold, it's more ambient. In future missions, we've discussed whether we'll have the capability to provide hot water. That'll be it's an energy cost. But in this case, we do provide hot water. I'm not sure if I do have a slide. Let me show you this. On space, if on shuttle, the water was hot. That was produced there. But we give the crew the option to reheat their food with hot water or to drink what we call ambient temperature water.
Okay, thanks.
Did I answer your question? Okay. You can see here a crew member on the space station is filling a drink bag. You can see there's a needle hidden in this area, and he's stuck his drink bag there, and he's pressed the dispense button, and then he's filling his drink bag right here with a happy smile on his face. Here's our flow path. Again, probably more detail than you care about, but for the ambient, we can dispense ambient temperature water, and this is what our microbial filter looks like, and this is what our deiodination filter looks like. And it's a combination of activated carbon and ion exchange resin. Then we also provide a whole bunch of miscellaneous connections so that you can connect things together that we have to build. But the key here for a space station is that we provide multiple barriers for the crew. The key thing on the potable side is that you want to make sure the crew is drinking something that's not going to make them sick. So we provide filtration, we provide heat sterilization, we have chemical oxidation, and we provide that residual disinfectant in the iodine, in the form of iodine. We also have a remediation ability on orbit. If somehow you were to see a whole bunch of bacteria pop up, we have, we've called them shock kits, kind of like you would for a swimming pool. We have bags of very concentrated iodine solution that the crew's able to basically inject into a contaminated, particularly the potable water dispenser, a contaminated area, and really clean that out in case we were ever able to see some microbial contamination. And that's kind of just a summary of our disinfection techniques. Here's our remediation bag, as I mentioned. That's our iodination bag. Using a 40 milligram per liter iodine solution. As I'm sure you've seen, like when you use iodine to clean a wound, it's very brown looking. Iodine is a strongly colored solution. So you can squirt that iodine into your potable water dispenser and clean out any dispense lines that you're worried about. Here's where I get to share what ickiness we talk about. A wastewater filter on the system can get very plugged, and we've had a problem with that filter becoming contaminated. That is the kind of contamination we don't want to spread throughout the water recovery system. Those are microbial biofilms that have grown on the surface of that wastewater filter. I always joke with my team that bacteria always win. They're very persistent, and we have to constantly keep multiple barriers to prevent microbial contamination. This really concludes the current technology portion of the presentation, and I'd like to acknowledge Catherine Toon and Rachel Edgerly here at JSC. They provided a lot of the material on the potable water dispenser side of things, and then Monsi Rahman and Lynn Carter provided a lot of the content for me for our current space station systems, and they're located at Marshall Space Flight Center. Okay, so before I continue, are there any questions on the current water recovery systems used on space stations?
Doesn't look like there are.
Okay. And Sydney, I know that we had planned for 10 to 11. Do you want me to finish this up in about 15 minutes, or do you want to go?
You can take your time. We've got a flexible schedule with your talk.
Okay. All right. Very good. So let me take you through water recovery systems for exploration missions, which is kind of the topic that's more near and dear to my heart. And I'm probably going over some ground that you guys have talked about, but it never hurts to repeat. The whole goal of what we call exploration life support is to duplicate the functions of the Earth in terms of human life support. On Earth, we have these huge buffers. We have our atmosphere. We have our oceans. We have land masses that help us regulate temperature. You know, I'm sure you've all heard the fairly irreverent saying that dilution is the solution to pollution, because you've got these large volumes that you can work with. Water in the environment becomes cleaner through natural processes, things like that. So we benefit from having this incredibly large, complex system on the Earth. But what we try to do through the development of life support systems is how small can we make these buffers for spacecraft and yet maintain extremely high reliability over long periods of time in hostile environments. And I saw that one of the outcomes of y'all's workshop is to develop a lesson plan leading to a high reliability, highly closed ECLSS system, which is exactly what we're doing. So, you know, it's a totally on-target task for you as to how can you close your systems and still be highly reliable without those giant buffers that we benefit from on Earth. Again, we've talked this slide. You've seen this. But again, water is really important. I'm not the slightest bit biased there. This is a chart I like to talk about. It gives you a sense of where things break even. We talk about the mass of a system or the cost of a system in terms of equivalent system mass, which is what you see plotted on the y-axis over here. Equivalent system mass kind of turns everything into kilograms. The mass of a system.
Karen, could you speak up a little bit?
Yeah.
Okay, great.
Is that better?
It's
okay.
my old ears.
Okay. The equivalent system mass of a system takes the mass of what something actually weighs. It converts volume to mass. It converts energy to mass through this lovely complex equation that our analysts have come up with. And this gives us a way to compare, a small heavy system to a large light system. It gives us a common denominator to compare systems to. So that's why we like to, our team talks in terms of equivalent system mass, or ESM. But what this chart shows you is the dotted lines are no water processing, where you have, like, say, a transit vehicle, which is the pink line, or a permanent outpost, which is the blue line. And this was a case where you're comparing a Mars transit vehicle and a lunar outpost in the study. When you don't process water, you can see in the dotted lines right here that the cost of your mission just increases linearly as your duration goes up. You get very heavy very fast because you're replacing water rapidly. However, if you close your water system, you start seeing a break-even out around 50 days. When you start recovering, it starts making sense that you're going to have less mass when you get to about a 50-day mission duration. That's why for some of our short-duration missions that we're talking about right now, excuse me, when our crews are only gone for maybe 30 days, water processing doesn't really make sense. But when you start talking about extended missions, getting past into the 90-day range, well, now it makes sense to start closing your water processing cycle and recovering water.
Hey, Karen.
Yeah?
I'm wondering, you know how when fuel becomes very expensive, all of a sudden we start thinking about conservation. We just retired the space shuttle. I'm wondering if you're seeing a resurgence in conservation now that we don't have that kind of resupply to space station.
Right now on space station, the major water consumption is crew drinking. There's hygiene, but it doesn't take a whole lot of water. Water consumption is the biggest factor, and there's no set limit. The medical community is what kind of governs water consumption, and we found that it's very highly crew specific. Some crew members drink a lot of water, up to 4 liters a day, and some crew members don't. They'll drink much less than that. So we haven't really seen a drop in water consumption because it's pretty variable to begin with. But there's no correlation right now to the ending of the shuttle program and water consumption. And I will tell you right now that's partly due to the fact that the perception, well, it's partly the fact that we let them drink whatever they need to drink, right? But the other part is that right now there is an incredible surplus of water on space station. It's hard to turn around without bumping into a water bag because the space station program made this tremendous effort to maximize water transfer before the shuttle retired. So they stuffed as much water as they possibly could into that vehicle as a risk mitigation in case the water recovery system broke. They wanted to be sure they had this huge buffer of water to get them through the repair stage. So if you were to look around space station, it doesn't look like there's a water shortage right now.
Okay, I got you. Plus, it's good shielding, right?
Yes, that's the other advantage is that it is a radiation barrier. We've had crew members use water and move it strategically around for those reasons too. Excuse me. Okay. Any other questions before I go on? Okay.
Can I
I
just
always
ask
throw
one
this
thing?
in when I
Sorry.
talk. No, go ahead.
So you said that the usage of water is very different between astronauts. If you got into a situation where water was becoming scarce, would you pretty much tell some of them to knock it out? I mean, would you begin to limit down to what would be considered the bare metabolic needs on space station?
I am sure if you got to that point that the medical people would start saying exactly what amount of water you had to use. Right now when you use the waste collection system, we have a flush cycle, so that takes water. There is a contingency waste collection system on orbit that you could use if the potties weren't working. So maybe you would go to a system where you wouldn't use the flush potty, you would use another system. I mean, I think if you get to the point where you're faced with there's no water left, you have to come home and deorbit, they would start taking those measures. I personally can't speak to what those exact contingency plans are. I'm sure they're out there, but that's not really my area. So in the terrestrial cycle, y'all have seen this. You have evaporation, condensation, precipitation, surface runoff. I stuck these two little things in because I like the water-wastewater part of it, where you take water out of a lake, go to a water treatment plant. You have a city sitting in between. It goes to a wastewater plant, and then the discharge is back to the lake, typically. Excuse me. An interesting factor in Houston is in Houston in the summer, and I'm speaking because of my Southwest regional kind of thing here, we go through frequent droughts in the summer. And City of Houston gets its water from two watersheds, the Trinity River and the San Jacinto River, that both feed kind of into Houston. And in the case of the Trinity flows between the Dallas-Fort Worth area and Houston. At low flow periods in the middle of the summer, where you might be in a drought condition, over half the water in the Trinity River is discharged from the city of Dallas as wastewater plants. So while we don't do reuse of wastewater in the United States right now, we sort of are if you think about it, because cities upstream discharge their waste into their treated effluent, not their waste. Their treated effluent, which meets all of the EPA's requirements for effluent. And that flows downstream to the next municipality that's using that water source. So particularly in the case of surface water applications, you are doing a kind of indirect water reuse at certain parts of the year. So when you take this terrestrial water cycle and you condense it down to what a spacecraft does, we're doing the exact same thing. We have condensation, we have evaporation, we have precipitation. All that stuff happens in a spacecraft just in a really small cycle compared to what's happening on Earth. And I've mentioned this. I've kind of highlighted the water piece of that big integrated ecosystem. The interesting thing about water, and one thing I like about it, is that our water requirements vary as our missions mature and our wastewater characteristics change. Again, on space station, you're half humidity condensate and half urine. That's all you got. Just to compare us to the air system, it doesn't really matter if you're sitting on the surface of Mars or you're sitting on the space station, your metabolic needs for oxygen really aren't changing. However, I can envision if we're sitting on a surface of Mars, where we're going to be for perhaps a year and a half or longer, hopefully someday. Sorry, I'm getting over a cold. I'm coughing a little bit. I'm sorry about that. Our wastewater characteristics are going to change. I tell people regularly that if we think we're going to be on a planetary surface and the crew's not going to take a shower, we're fooling ourselves. And that as engineers, we have to provide that capability for the crew to take a shower, because once they have gravity and water will run to a drain, they're going to take a shower. And either we're going to give them a shower or they're going to make a shower with a hose and a bucket. But it's going to happen, and we might as well engineer and plan for it as opposed to having to face it when it happens. So that's why I talk about how wastewater characteristics change as our mission matures. This gives you a sense of some of the missions we might be working on in the near future. I broke a rule and I used the acronym MMSCV. That's our current short-duration vehicle that we're working on right now. It is, again, a short duration. It'll take you initially to a space station, perhaps, or a close application. But in both cases, it's going to be an open-loop water recovery system. We don't expect right now that we'll have any type of water recovery in that vehicle. It'll be based strictly on what I've called here urine pretreatment, which is really that urine stabilization. It's pretty critical so that we don't have breakdown of our waste products on orbit. If we're not going to treat them, we have to store them, and we really don't want them breaking down if we're storing them. Disinfection systems are also critical. You're going to have stored water sources on this open-loop water recovery system. This is the one that just doesn't make a mess. There's not a good rationale for having a heavy water recovery system when you can just store the water. But you still have to ensure the water is microbially safe to drink when it's been stored for a long period of time. Then you're also going to have some kind of contingency operation, perhaps, where you have to recover water. That mission will evolve perhaps to maybe a transit vehicle or some kind of shorter duration, maybe a lunar outpost where you're there for just 90 days, some sort of limited staffed mission where you're not there as a permanent presence. You're going to come and go from whatever your transit vehicle or your habitat might be. In this case, we envision perhaps a partially closed water recovery system where you have to be able to turn systems on and off. This is particularly suited to what we call physical-chemical system development or systems that rely on physical treatment processes or chemical treatment processes. They typically use power, and they can be stopped and started. They also typically need post-processing systems. These systems then evolve into the fun area, really, the really interesting things, where it's a long-duration habitat, where you have a fully closed water recovery system. This is where our additional water sources come in. I'm sorry, I left the L out. That's supposed to say laundry, not laundry, and food production. You know, for years we've talked about if you have this fully established, evolved habitat where you're growing biological processes like Ray Wheeler spoke with y'all about growing food sources, initially perhaps salad crops, but then perhaps moving into more of your closure on your food production side. If you grow peanuts or soybeans, you have to then turn that plant thing into food products. And who's going to clean the peanut butter maker or the tofu machine? So all of these the need for water grows as you make this highly evolved, closed environment. And the waste pieces change. Removing the oils from a peanut that are produced by peanuts that are left behind in peanut processing hardware is a very different thing than just removing the salt that comes from crew urine and sweat. So you get these complexities that change, and the water treatment processes that are most advantageous or suited change as well. It gives us more options for treatment technologies, some kind of attractive things like biological systems, things like that. This is a water quality comparison that I like to show up in these kind of presentations. What I've done is taken some data from an advanced plant, water treatment plant called Water Factory 21 that's out in California in Orange County. These are kind of some markers that we use for how we define water quality. The influent to this water reuse plant in California is treated waste from a wastewater plant.
So it's taking treated effluent and looking at making water that meets potable quality. If you measure the total organic carbon of the water going into that system, that's how many milligrams of carbon there are in the system. It's about 10 milligrams per liter of carbon. Comparing that to what spacecraft wastewater is like that we're trying to turn back into potable water, we have 400 to 700 milligrams per liter of organic carbon in our waste. Another measure of kind of how contaminated water is chemical oxygen demand. That's how much oxygen it would take to break down all of the organic material in the water. The chemical oxygen demand of Water Factory 21 is about 39 milligrams per liter. Our chemical oxygen demand on the spacecraft is 1,400 to 3,000 milligrams per liter. pH is also very different. The pH is very neutral typically in most terrestrial plants, whereas on spacecraft, our influent pH, if we don't add a highly acidic agent to stabilize the wastewater, runs between 8.5 and 9, which is slightly basic. That's because urine breaks down when you don't stabilize it. The urea in urine turns into ammonia. We all know what that smells like. And that also, ammonia is basic and drives pH up. Conductivity isn't too different, but it's a little bit different. That's a measure of how salty the water is. And again, in total dissolved solids, they're fairly comparable too. This is the sodiums and the chlorides and the sulfates and things like that in our water. So those are on a comparable basis here. So as your students are designing reuse systems for spacecraft, kind of the guiding principles we go by is we, of course, want to minimize volume, mass, and power. We want to achieve high recovery of water. We really want to limit chemical additions and those what I would call non-regenerable components. On space station, the ion exchange and absorption section works very effectively. However, once it absorbs up to its full capacity, you have to throw it away. When those type of systems are used terrestrially, they can be regenerated. However, the complexity of regenerating it with very strong acids that are at high temperature for the carbon, it's hard to implement that on a spacecraft. So when I say non-regenerable components, those are things that you use and then have to throw away because they're exhausted. And then always the fun thing is gravity-independent operation. When you have a transit vehicle or going to an asteroid, your systems have to be compatible with microgravity. It's a challenge in terms of the liquid gas movement. You have to keep those things separate in microgravity. So just kind of some little cartoon pictures for you. Open loop systems, the guideline in our medical operations document that we designed to is 2.5 liters per person per day of water. Again, some crew drink more, some crew drink less, but on average we design to a use of 2.5 liters per person per day. We have potable water storage in our open loop systems. We provide that residual disinfection. Typically we're going to pass water through one of those 0.2 micron or smaller sterile filters that would just be a second barrier for microbial contamination. Crew uses the water to drink. We also flush our potties. In open loop systems, we're going to stabilize our urine, store our wastewater, and eventually throw things away. Another thing that we've talked about, and it's really some clever ideas, Michael Flynn, who was your original presenter today, has done some really interesting work on disposable water recovery systems that are there for some contingencies. If something really goes wrong, what can we do to keep the crew alive to get them home? So Michael's done some really interesting work in that field. I'm going to talk about that here in a minute. I have to show you all gross pictures, and it's really blurry, which is probably good, but if you can see, this is a valve we took out of one of our wastewater collection systems. Everything here, all that white stuff, is precipitation and bacteria that have all collected in our wastewater system. In our homes right now, your waste lines in the home that you live in is probably a 4-inch pipe in the walls of your home. On orbit, we have quarter-inch stainless steel lines. Keeping those lines clean is our big challenge and one of the worries we have. So when we stabilize wastewater, our goal is to prevent that biofilm development from bacteria from colonizing all those lines, and then to prevent precipitation in the waste collection system, because urine, sometimes solids in urine, tend to want to precipitate out. In terms of what we're working on in technology development, we're looking at lower toxicity stabilization systems. Right now, the chemicals used on space station are fairly toxic. Strong oxidizers, strong acids. We really want to reduce the toxicity of the components that are used there to reduce the hazard to both the crew and the ground processing team at Kennedy Space Center. We also would like this to be compatible with multiple technologies. If we're going to need to stabilize things to keep our wastewater collection lines clean, that technology needs to be compatible, whether we're going to use a biological treatment system or if we're going to use a distillation system or a membrane type system. This is some data that we took out of a study done here by a chemist on our team, looking at the maintenance of silver in water distribution systems. You can see how silver wants to. We start out at a very high concentration. On the y-axis, we have the log of C over the initial concentration. Concentration at the time divided by our initial concentration. At 20 hours, we have most of our silver still in solution, but we see a very steady decrease in the concentration of silver over time. Silver wants to plate onto the surface of metal, of stainless steel tubing. So silver is hard to use as a disinfectant long term. You have to be able to resupply it. This is the work that Michael Flynn has done with contingency water system. He called this his lightweight contingency water system. And really, he looked at a commercial system. It's a forward osmosis bag built by a company called Hydration Technologies. I believe they're in Nevada, but I'm not positive about. But they build these bags for the United States military. I've actually seen them at Costco now. In this case, it's really kind of clever. There's this white thing in the middle of the bag. It's a two-sided bag with a membrane. Commercially, if we were to go buy one, we would perhaps put lake water in on one side. And that membrane is going to allow water from the dirty side where you put your water in to go and transfer to this solution that's on the green side of that, the back side of that membrane. It's just a simple experiment in forward osmosis, just like we talk about in high school science classes. Water wants to go and dilute the highly concentrated sports drink solution that you inject on the green side. So the dirty water ends up, it's dirty, but it has a lower osmotic potential than this highly concentrated sports drink you put in here. So water flows across that barrier to dilute the sports drink, and then you can drink the Gatorade or whatever nutritional drink you end up designing to put on that side. So you're not getting pure water out of it. You're getting some kind of hydration solution, fortified drink, as Michael puts it. But you are able to provide an emergency source of water. Michael had looked at applying this instead of just using river water, had looked at taking raw urine, passing it through a small activated carbon filter, and then putting that urine onto the dirty side instead of, like, if you were seawater or lake water, you could actually put urine in here to provide that contingency water for when you have a true emergency and have to keep the crew alive to get them home. Okay, from open loop we move into what I would call a semi-closed loop. And this is what we have on Space Station right now. Our loop is, we get about 85% of the water back. We recover 70% of the urine and 100% of the humidity condensate, averaging about 85% as a rule of thumb. In this case, we'll start here at the potable water storage. Again, we have the disinfection step. The crew uses it for whatever hygiene processes. In this case, where I show the sink in the shower on space station, this is done through like wet wipes or squirting some water onto a towel. Perhaps if you had a 90-day mission on the surface of the moon where you have some gravity, you could actually have a sink. It just kind of depends. Where it's a short mission where you don't need to fully close your system, but you have gravity, you can have some more water sources. Again, you probably have urine pretreatment. When I was much, much younger, I always wanted to get away from this urine stabilization step, but I've come to realize that it's very hard in some way to collect waste at the waste collection system and keep your lines clean without some kind of pretreatment. This is a really interesting area of study. It can be done in a lot of ways. There are a lot of creative ways that we haven't implemented yet. Perhaps the answer is just a very effective flush. Perhaps the answer is using perhaps something like hydrogen peroxide that breaks down. Perhaps there's a clever way to apply UV treatment to this. There's a lot of room for creativity. It's like the least glamorous part of the water recovery system, but there's a lot of areas for creativity here that have impacts throughout the system. So however you stabilize your waste to get it from point A to point B, you get to your wastewater storage tank. You then have a primary treatment system followed by post-processing, because you never really get to potable water in one step. Usually when you're in a semi-closed loop, this is the system that you're turning on or off, and you're able to typically be a physical-chemical process. Nearly every physical chemical process I can think of produces some sort of brine. You don't recover 100%. There is some water that you've concentrated all your waste into and you're going to probably discard. So you discard a percentage of your waste. That's why we call it semi-closed. And you have post-processing, disinfectant, and you back to your closed potable storage. So here's where we go kind of to show you how the wastewater composition changes visually. Here's our ISS system where we're half humidity condensate and half urine. You have a very low pH. It's corrosive in this case because of what we use to stabilize our waste. And we have a very high calcium concentration because astronauts excrete more calcium because of microgravity and the bone loss. And we have this concentrated waste system over here. This is, as it transitions to that long-duration mission, we have a more complex wastewater. We want to go to a greener stabilization. We have surfactants now because we have showers, perhaps, and laboratory waste. So we're going to have personal care products in the waste stream that we didn't have before, like shampoo. We have toothpaste concerns, things like that. So now our wastewater distribution has really shifted a great deal, where a big percentage is from hand washing and showers, over half our water. And this doesn't even include the evolution where we include laundry in the system as well. So just to give you some visual pictures, this is, let's just say, what wastewater looks like. It's kind of, there's no solids in this, which makes it prettier for you guys, but this is a mixture of what urine and humidity condensate would look like, kind of in a light yellow-colored wastewater. A distillate, if you're running a distillation system where you've essentially boiled your water, or if you have a membrane system where you've used pressure or concentration to treat waste across the membrane and essentially filter the water, you get a permeate across that membrane. You have a very clear, visually clear water. Again, roughly 70 to 85% of your water goes here through physical chemical processes, but you've taken all of the waste that's in that and concentrated it in your brine, which is now this murky amber-colored liquid that you tend to throw away in a semi-closed system. Just images. We have done work with forward and reverse osmosis systems. This system was built by a team at an Ames Research Center, Michael Flynn's team at Ames, and sent to Johnson Space Center for testing. That's a young woman on my team who is the project engineer for that system. We also have done some work looking at a different type of distillation system. This is a cascade distillation system, which has some energy efficiencies because it has multiple distillation chambers and recuperates some of the heat of condensation. So it has some energy efficiencies compared to the distillation system currently used on space stations. So again, back to our semi-closed loop that we saw here. We talk about post-processing systems. There's different ways to do this. Our catalytic oxidation that's currently used on space station uses catalyst beds, these little beads that typically have a noble metal, either platinum or palladium or ruthenium, on it. And that catalyzes some of these reactions that break down the organic materials at high temperatures. They're very efficient and have the benefit of disinfecting water, but they are high energy because they're at a high temperature and pressure. We would love to get that temperature and pressure down below a boiling point because it increases the reliability and safety of our systems. The other type of post-processors we can use, this is a nice clear ion exchange bed that allows you to see what's actually inside of it. The amber-colored plastic beads are coated in a chemical that likes to take up that charged species, that calcium or the sodium or the chloride. And these are just commercially available resins that are made by some of the major chemical companies that we purchase for our testing. Some really interesting future work are in photolytic systems, using UV light either directly for photolysis or using titanium dioxide photocatalytic systems. There's just some really interesting emerging technology in this area that's usually generally characterized as advanced oxidation processes in the water treatment field that have tremendous potential with some more technology development. They're not quite ready for implementation, but there's just some really interesting areas looking at light sources to use for the breakdown of organic materials. And then we get to the final option where we have a closed-loop water recovery system. Here we bring in what we've called it various things over the years, but right now we call it brine dewatering or brine water recovery, where you take that highly concentrated waste and attempt to recover the water from it so that you can get full closure on your water recovery system. Other primary treatment systems now, when you talk about a closed-loop system, it brings up the potential for biological water recovery systems. I'll show you this wastewater looks a little different than that first one I showed you. You can see how turbid it is. The cloudiness is due to the presence of surfactants in the system. I'm sure y'all have all seen a soapy water, how it looks a little cloudy. That's what you see here, the suspended solids from those surfactant molecules from the soaps, shampoo, and things, personal care products. A biological system harnesses the power of bacteria, just like our terrestrial wastewater plants do, to let bacteria basically eat all the organics in the wastewater and turn it into something much cleaner than it started out. Right now we have an advanced technology project looking at a biological treatment system that we're working with some engineers at Kennedy Space Center here at Johnson, as well as researchers at Texas Tech University, to design the next generation of this biological system. This picture shows you 3 different types of systems we have tested here at Johnson Space Center. Our newest ones are aerobic systems that use membrane tubes to aerate a closed system and keep the bacteria alive. So all that water systems and all the ways you can design different water systems for the evolving mission needs all tie back into the spacecraft water cycle, where you've got the crew generating waste, you have to recover urine in some way, shape, or form. Perhaps you mix the urine with your wastewater from the hygiene systems coming in here. here we show it separate, but there's certainly a way to certainly mix it as well in your architecture. You have potable water processing. Product water is going to go to the oxygen generation, as well as back to the crew for use. The crew is breathing, making condensate that we have to process. So everything gets tied together in our wastewater system. Some interfaces to think about as we mature in our missions. Right now, water recovery is primarily working with air revitalization, connecting those two systems together. We also interface with habitability systems, but ultimately we'll interface with crop production systems, our solid waste systems, food production systems, as well as ISRU is in situ resource utilization. If we get to a exploration location where there is water present on the surface, it's unlikely that we would drink it directly from the recovered place. We would have to take that water that's recovered from the planetary surface and treat that as well before the crew would use it. So we have a lot of interfaces that bring us to a fully mature water recovery system for spacecraft. Again, as an overview, we go from a short duration, perhaps just a surface sorting mission, where you just have our contingency systems and ways just to keep the system going for your stored system. Lunar outpost, which has to recover water, but be able to be turned on and off because that's going to be a shorter duration stay. Then we get into our extended bases and our permanent presence, where we have things like biological systems that become an option for wastewater treatment. And again, from closure, wastewater volume, and our wastewater sources are all increasing as we move across that spectrum. With that, that is the end of my very long presentation. I'm happy to take any questions that anyone might have.
All right. I was wondering if you had, so let's suppose you found water on Mars, and probably it wouldn't be on the surface, but somehow you'd find some water on Mars. So you'd have to treat that as if it were wastewater in terms of, purifying it. Is that basically correct?
Correct. That I would make the assumption that any water that you recovered through, getting it out of the rock or however you're going to do that, that's a byproduct of your fuel production, perhaps, would all go into the water treatment system before being consumed.
Hi, Karen. I was wondering, so you spoke a little bit about the biological options. I was wondering if there was any work on hybrid physico-chemical biological type architectures where maybe the brine from a physico-chemical process could be treated using a biological process.
We haven't looked at treating the brine in a biological process yet. The primary thing we're looking at right now is using the biological process as the primary treatment system. That gets rid of anywhere from 85 to 95% of the organic material. We can also use bacteria to take the ammonia that's generated from crew urine. In this case, we want that urea to break to ammonia. The ammonia can be through bacteria. There's bacteria called nitrifiers that use that ammonia as an energy source and turn it into nitrate, a different nitrogen form. You can then cycle that nitrate back around to the bacteria that break down the organic carbon, and instead of them using oxygen as their oxygen source, they can use that nitrate, which is NO3, and then you get nitrogen gas back off. So what I tell like fourth graders, and it just grosses them out, that you can, you're urinating and making urine, and you have this urea that breaks down to ammonia that bacteria change back into nitrogen gas for you to breathe. So you can have urine one day and have breathing gas the next day if you design your system correctly. However, biological systems can only do the organic material, and then they can do the ammonia and a few other inorganics, but in general, the chloride and the sulfate and the sodium are all going to be left behind from a biological system, and you have to integrate that with a physical chemical system. So pretty much any biological system is going to be a hybrid system. It would be interesting to look at a biological system with a very high-strength brine waste, and we have never done that. to think about how you could design a system to do that. It'd be very small and compact because the water would not be very, very much, but it'd be interesting to look at.
Okay, excellent. Thank you. Are there any other questions?
Quick question. Karen, I was just curious, are you able to dump the solid waste like brine into deep space, or is that not allowed?
Right now, there are planetary protection. If you're on a planetary surface, you certainly can't dump it. Right now on space station, there is no way to dump it. Okay, let me actually, I'll go through this in a more organized way. On shuttle, they had a wastewater tank that their waste collection system would put the urine into, and they actually did wastewater dumps periodically on orbit. And you can go back probably and find YouTube videos of like this stream of ice crystals coming out of the space shuttle. There was a vacuum vent line that would allow you to dump waste overboard on space shuttle. There is no capability for that on space station because it's propulsive. Believe it or not, when you vent water in microgravity, it can change your orbit a little bit. So that propulsive effect, they don't want that on space station because it affects the microgravity experiments. So they were never given that capability. So instead, right now, waste is packed right now into the Progress vehicles. After Progress vehicles from the Russian Soyuz, the Progress vehicles are unpacked of all their cargo and then filled up with trash, and then deorbit and burn up on the way to the ground. So that right now is how waste is disposed of. They just stick it on Progress and it burns up on reentry. As we went to a planetary surface, there are a lot of planetary protection policies in place that I'm not really an expert on, but I do know that we've talked a lot about how you would stabilize waste to store it and not have to dump it or leave it behind. Did that answer your question?
Oh, that's very good. Thank you.